So the first session we're going to listen to is dealing with AI scaling laws. I think this is going to be very, very interesting for you. Just one second, let's get this up here. Okay, so speaking on this subject, I'm very pleased to introduce Brian Wang. Brian Wang is a futurist, thought leader, and a popular science blogger and YouTuber with more than 1 million views per month. Brian covers space, robotics, artificial intelligence, anti-aging, nanotechnology, and much more. He has written over 30,000 articles, and Brian also advises corporations and invests in fundraisers for startups. So, Brian, thank you very much for being with us today, and we'll turn the session over to you.
Thanks, David. So I will now share my deck, and then we'll go into my presentation. Yeah, so I'm going to discuss AI scaling and scaling laws, but not going to be like a dry technical talk about it. It's going to be more using some of those principles that things are scaling and improving. So I'm going to discuss that, where AI is today and how we got there, and how the growth of compute and data has gotten us here, and what are some highlights of what it can do, and why it's valuable. I'll also discuss how lowering costs is actually good for the industry. I will indicate why I think it's going to go to spending, going to go from $300 billion per year now, rapidly, maybe next year, year after, to $1 trillion per year or more. And that's going to be partially related to Pascal's wages and other things. So these are the 5 areas, and we'll just get into that and then move on. So in terms of why it's so powerful, Reid Hoffman, who co-founded LinkedIn, recently said he asked Replit, which is a company valued about $3 billion that does, it's a wrapper and does stuff around the models to create applications and coding and that kind of thing. He asked it to create a version of LinkedIn, and it made a surprisingly functional prototype out of that, which can be seen that on the right was kind of the result it made out of that when he asked it to clone LinkedIn. There's people, all kinds of stories like this where, my wife, who did not do any coding or learn any programming, was able to use some of the tools like Replit to make a business video game and that kind of stuff in a couple of hours in a session. So it's very capable and getting to the point where it will make, games, websites, the agent aspect of things. But I'm not going to go into that in detail, but it's very powerful. But what I want to focus on is more the coding aspect, and then also I'll briefly mention things like robotaxi and human robot. But the coding aspect, with Copilot, with the other tools, all the studies are saying that you're already 2.2 times more productive with that. ARK Invest and others are talking about 10 times by 2030. For me, the possibility is fully automated and validating programs where you give it your request and then it goes off and does it. So what do I mean by that? There are 40 million developers in the world making 10,000 to 100,000 lines of validated code a year. So then you're in the range of 400 billion to 1 trillion lines of code. So then if you had an AI data center fully, with the latest, NVIDIA B200, that kind of stuff, they talk about generating 12 billion tokens per second. So then even if it took you 12,000 tokens, like we do some agent thing and do a bunch of work and stuff like that to generate a line of code, that 1 million lines of code per second from your system would then generate 32 trillion lines of code, or more per year. Although you would then blow away the from one massive AI factory, the line of code generated by all of humanity. So that's the kind of game-changing thing that can happen. And one of the things is that synthetic data, which is like you extend out the data that you've gathered statistically, synthetic data works really well for coding and math. So if you generate the compute, then it's all going to run out of data. For coding, synthetic data works. So that means that coding and math will need to be solved. And once that happens, then we could have this software intelligence explosion, which would be irrelevant in terms of like hallucination, because you would validate it, you'd compile it, you'd run through verification to make sure you got what you wanted. Okay, so a lot of people concerned about DeepSeek, OpenAI, and things made cheaper. So Jevon's paradox, economic law, rule of thumb from many decades ago. Jevon paradox says when something becomes cheaper or more efficient to use, people use more of it. We saw that with internet, personal computers, all that kind of stuff, where things got cheaper and we ended up using more. The industry, the market became bigger. So for AI, it'll be more AI, more agents, more reasoning, more tokens as things become cheaper. And DeepSeek was part of a continuing wave of things getting cheaper. That when you look at the inference costs, going back 2-3 years, it was 100 times more expensive to do things, and now it's 100 times cheaper. And the fact that it was DeepSeek in China versus Claude or OpenAI that was doing it was the only novel thing. It was like expected that we're going down this lowering cost scale. For what David was talking about, when you're investing in companies, you have to make sure that it's going to get cheaper. So whatever company you're investing in has to be immune to the fact that next year things could be 100 times cheaper, 1,000 times cheaper for AI. They have to be able to adapt quickly to it. So whatever business model moat they have has to be, this trend must make them stronger versus weaker. So then why do I say that we're going to get to $1 trillion or more of spending? So it goes to Pascal's wager. Pascal's wager was about, is there a God? Do you need to act like you believe or not believe? Because if you're right, then you go to heaven. If you're wrong, if you believe, then things are still okay. So Pascal's wager for AI. A CEO investing in AI is a rational bet for them to assume that there's an AI God. The AI will totally work out, and they'll win. If they're wrong, they can still win with technology advancements. Like I still make cloud stuff. I overbuilt a little bit, not that big a deal. And when you look at their finances, it is something where they can afford to do more. They still have free cash flow when you add up the top 4 or 5 big tech companies of $400 to $500 billion. So they're $300 billion plus their free cash flow. Just to say, from my super profitable business, I'm putting all in on that, not saving anything back. They can go to $800 billion, and they're growing at 15% or more per year. So then the year after, they go to $1 trillion. And that's not tapping into the sovereign wealth funds to get even more trillions on that. So that goes through this. And I did the analysis for Microsoft, where they can go from 80 billion per year now to 200, $300 billion in a few years just by themselves. So I feel that the 1 trillion per year spent on AI is pretty much assured. And Microsoft announced on the earnings call they made 2.5 times more from AI revenue in a year. So the revenue growth from 5 billion to 13 billion per year when they separate out their AI. So their investments are more, spending 80 billion. But 2 years ago they spent say 10 billion, and said they're making profit on the investment they made 2 years ago. They just have to front load things in order to get the AI stuff going. So the other thing is that AI scaling is getting faster. So we had Moore's law, things doubling every 2 years for a decade. And then for the last 12 years on the AI side, between 4 to 7 times more compute going into AI for the last few years. And compute translates into the performance of the models with the scaling laws of loss function. So 4 to 7 times. So that was what's happening up until 2024. And then, but there's some limits to that. Like you can get 10,000 times more based on certain assumptions around how much data we have, chip production. So if you get rid of, I view these as bottlenecks, not as hard caps. That if I solve the data problem, then I can go higher. I can go up to say, get up to chip production. I can go up 5 times more. But if I solve both those problems, then just dealing with data scarcity. Sorry, that first one was power requirements. So if I solve each one of these things, I can get up to 100 times, 1,000 times more. And I think these are not, again, hard limits and can be discussed in more detail in a later session. So for that power law, as we get more compute, this error rate goes down to get to the level of what they call irreducible error. So if I have 1,000 times more compute, the loss function says, you get to 70% less errors. And then if I get to 10 million times more compute, I'm at 60% less errors. And then also the number of tokens of data I need kind of is the square root, roughly, of that training increase. What happened before was going from GPT-2 to GPT-4, we went up nearly 500,000 times, and that halved the number of errors. So if people have used those models, GPT-2 versus GPT-4, is like a crazy differential. There's also emergent properties that came out of that. And then we had a 10x gain from GPT-3 to GPT-4, and again, that reduced the error by 20%. That can kind of translate to IQ. Like if we say that right now we're at 150 IQ for these systems, if you had another leap of reducing error by half, IQ might go to like the equivalent of 200 to 300. But again, that's the kind of like difficult thing to get to. You can ask me about it in the Q&A. So I'm going to also say now, so I'm saying that we're going to go to $1 trillion per year spending. The spending keep going. It's going to make money. It's going to solve coding, which is a $4 trillion global market. Like 1.5 million for developers and consultants, 1.5 trillion for software, and then 1 trillion, 1.5 trillion for cloud. That's a huge market if you solve coding. If you multiply it by 100 times, that's huge value there. So I'm going to say that XAI is the winner, not because I'm a fan of Elon or anything like that. It's because when I look closely at what they're doing, they have a insurmountable lead with certain things that they've done, at least for the next year or two. And I'm going to say that next year or two is what matters. So one is that they've installed 100,000 chips, H100s, in their Memphis data center for the training of Grok 3. And then when they announced Grok 3 in February, they said they installed another 100,000 chips, H100s and H200s. They already had 200,000 chips. And those chips all work together. So the AI chips and AI data center need to work together because all the memory needs to look to the GPUs as a single memory. That'd be what they call coherent, right? And what XAI and Tesla did was that they rewrote of the 7 layers of Ethernet protocol, they wrote the 3rd and 4th layer into hardware, which let them get microsecond lag times on communication instead of milliseconds, which lets them make coherent millions of chips versus previously for the last 2 years since GPT-4, everyone's been stuck at about 20,000, 30,000 chips being coherent. This is for NVIDIA chips. Google has a slightly different thing because they use GPUs, but still there's a limit on this communication issue. So coherent memory beyond 30,000 chips. And the 100,000 chips in 90 days, Jensen Wang on a video said that everyone else was taking a year to install the chips. So if they go through 2 generations in the next year, and the other guys are still installing the chips, then they won't be able to compete. And I'm looking at what's being installed where to go over that. So another example, when they released XAI to show that they went from, took OpenAI GPT-2 at the beginning of this chart in 2019 and GPT-4 in 2022, and on the left bar is the total training flops. And XAI started a year ago, went from Grok 0, Grok 1, Grok 2, they caught up in the training compute. And then 15 times more compute for Grok 3. So Grok 3 in the chart, it goes off the scale. And I'm going to say Grok 4 goes up 12 times. And then Grok 5, early next year, will be 50 times as much as Grok 3, or 750 times more than Grok 2, which is before we were at that 4x, 7x thing. So that's like 4 years of advancement versus 2 years, just by multiplying 5, 5 times 5 is 25, 125, etc. So Grok 2, Grok 3, 15 times more compute, Grok 4, 12 times, which is 108 times more compute from Grok 2 to Grok 4. And that's going to be 12-month gap. Grok 2 came out 6 months before Grok 3. I'm saying Grok 4 will come out about 6 months after Grok 3. So 1 year after Grok 2, we're at Grok 4 with 180 times the compute. And then I'm expecting that. So, and then I have the exact number of flops of compute and stuff like that. It's going up like crazy. And then there's, when that happens, you have to consider the data aspect of things. So I have considered that. And they showed that, they're installing the 100,000 chips faster, which again is an issue of how fast they can install this industrial capability. They are using mobile gas turbines. So the location that they have is able to access 1.2 gigawatts of natural gas. These turbines from a subsidiary of Caterpillar, if they dump 60 of these 16 megawatt turbines, that gives them their gigawatt. And then roughly rule of thumb, about 1 kilowatt per chip of power needed. So 1 gigawatt would let you have 1 million chips. So about 9-12 months, I'm expecting them to be able to get to that 1 million chip level. So they've already started this construction. They're installing 200,000 B200s. I've seen the environmental authorizations for them to install these things. So that's what's happening right now. So I worked this onto a table showing exactly what I expect each group to install what at what point, whether they've got the chips delivered, whether they got them installed, then how long they can do the training. So the right two columns of delivery installed, how long to train, what chips they're using, the number of days of training, and then the chip years of that. So I can get quite precise about what month I'm expecting which model to come out. And then so we already had the Grok 3, Gemini 2.5, Llama 4, the O3 and other models from OpenAI. So I think the next major one to be Grok 4. There could be these interim models, but they're not steps up in training. And there's a delay with GPT-5. I think they may be looking to switch out to 30,000 B200s in order to get that delay, in order to get some jump in their compute capability. Because they have the issue of not being able to get 30,000 to work together with a networking problem that they have to recreate over a few years. There's also algorithmic improvements, which is kind of like the thing that DeepSeek did. So when we have almost compute scaling, there's also this algorithmic improvement. So you get a lot of bang from the algorithmic improvement side. And that's something that could improve a lot if I just use these things better. There's also the inference side. So there's training, and then there's inference. Inference being the model is now learned what it needs to know, and then you're using it to think about the problems where you're asking it things. Again, I like to harp on the Elon Musk company, but Tesla is making all their cars with an inference chip inside. Their next chip will go 10 times the performance of that. It'll be in every car, every Cybercab, every Tesla bot, and then they'll upgrade their own chips. So they are full stack, making their own inference chips as well as training chips. And there's potential to have 100 million of these inference chips in their cars and in their bots by 2030. And the industrial takeoff would be if they use bots to make more bots, then this production level could even increase beyond that. So AI is getting to improving AI is another takeoff point. So the coding side, and then that is part of the AI improving AI. So software and algorithm explosion, software lines of code, better algorithms, and that gives a huge increase in capability. There's a gain of 200 times when you go from software, operating system, firmware, application, to going directly into the hardware, into the ASIC FPGA, where it can encode logic into the thing. So there's several of these points where if you can get AI to handle the complexity of making the move from Python to assembler machine language, from that into hard-coded hardware, you'll get a huge gain out of that, which again, you can apply into your data center to accelerate your improvement. And then there's also issues of chips and data availability, which is a more complex topic I can discuss. And then that industrial explosion where things get built a lot faster because once you have superhuman coders, superhuman researchers, then you get to full automation, which I think could happen earlier than this projection. So they have it in 2034. And then you can have this takeoff in terms of like the wealth created in the world and how many things we make. Yeah. So that basically is it. I'm open for any questions.
Okay, thank you very much, Brian. Very interesting session. So one question is, do you think to some extent AI will be a winner-take-all situation? Is it that the AI algorithms learn better and become more useful the more users there are? So to what extent is having a large group of users enhance the performance of AI and cause there to be, a limited number of winners?
For particular domains, like if we're replacing Google and getting a large number of users, then one could use that with network effects to become more dominant and have a winner take most situation. But because for that use case of, like we're right now, like we're people using ChatGPT more and how many users they have and that kind of thing, they're far in the lead right now in terms of like having, 400 million, 500 million users versus others. But Meta is going to get their billions of users onto their AI. And then if you're already hooked on Facebook or I'm already using Google Mail, they will give you a good enough AI and they will try and keep you there. So in that way, there can be multiple winners based on like how many minutes you spend on each application.
Okay. Okay. And then if you wouldn't mind going back to your slides, one of the earlier slides, maybe around the 7th slide, we talk about the loss ratio. That was a very interesting slide, but a little bit complicated. So I have some questions about that.
Okay, let me go back up. Sorry. Okay, so we want to go back to the 7th slide. So there's this thing or this table.
Yeah, maybe even let's see what slide is before this one. It's just
this is constraints on power and data. This is AI scaling.
Okay, can we go to the constraints one? I think there were some questions about that too.
Okay, constraints. Okay.
Yeah, maybe you can make that a little bit bigger.
Okay.
So let's see. Maybe can you just walk us through again, going from left to right, what's going on here?
So in order to build my AI data center, which is what to give me all the compute, I need to have energy, that gigawatt of power, right? Or right now things are at 100 megawatts, 300 megawatts. So you need to have enough power in order to, and that rough rule of thumb of if I want 1 million chips, I need a gigawatt. So here they're saying the power constraint is that we can get to 3 to 5 gigawatts of power before we start hitting a limit, right? Where you have some construction problems. Although I've looked at that problem more closely, and definitely we can get natural gas, all these portable turbines, getting up to 10 gigawatts or more very quickly. And then longer time would be like if China was to build 100 nuclear reactors all in one spot, right? Then I could get 100 gigawatts in that one spot, and then I could have 100 million chips, right? So 10 gigawatts. So first step is power limitations to get to these multiples of capability in terms of compute. Then chip production. TSMC only makes so many wafers. So even though I want to have 100 million chips, TSMC only makes 4 to 5 million of their latest GPUs, right? They only make I think they made 3 million last year, and they're going to try and make 5 million this year. There's limitations on memory, high bandwidth memory, the stacked memory that they use. They're in the chips. They don't use all their wafers for AI yet. They're actually a small fraction. There's something called interposers, which is a communication layer that limits their production. So in 3 to 5 years, they can make 10 million chips, right? Which would then be enough for a 10 gigawatt facility, right? So these are each constraints of like, how do I get to 100 million chips? I need to get to TSMC or someone else has to solve with not using interposers or solving for the production, getting more production out of it. So there's limitations about how fast that can go based on the chip production. And then we know how long it takes to build a new fab. It takes forever. And then data scarcity. Once we use up everything on the internet, that's like 500 trillion tokens. There's various things around data, but then I can use data more. I can overtrain on data. I can get more video data. So on video data side, the solving a robotaxi, they're at about 4 billion miles. If it takes you 1 minute to drive a mile, then that 4 billion is about like 8,000 years worth of video data, right? So, and then that basically was 1,000 times less efficient because it takes a human, 8 years or less, or a magnitude to learn how to drive, learn how to, be a person, do things, and then also then learn how to drive. So the AI was 1,000 times less efficient, but it didn't matter because you had a million, 10 million vehicles all gathering the video data to spread out the learning. Anyway, so power, chips, data, and then latency wall refers to again a communication networking issue that again is another limit or constraint. But there's ways to work around these things and ways to manage them. But this is so just improving 100 times a year. You'll says, when do I hit the power constraint problem? I can hit that problem in 2 years instead of 5 years by going faster, right? Then I have to figure out how to get more power. And then I have to figure out how to get more chips, right?
Okay. All right. And then if you can go to the next slide.
Okay.
Or maybe it was one more, the one that talks about losses. Yeah. Yeah, this one. Yeah, some people didn't understand what's going on here.
So it's the formula is based on how much compute I have, right? Then how much loss mean. If I have a loss function is, I know I'm comparing what's good versus bad, what's better versus worse. So, in chess, I know, okay, this is a winning position. I make this move, I make my position stronger, I can score it. So I know what's better or worse for this. Same thing for coding. I know that this program is better than this other program. And so I can then create a loss function of worse to better to perfect, right? So by the more compute I have, the more I can drive that to a better answer, less error, a better result. So that's the loss function. You create a continuous ability to compare, and then I can then use the compute to drive myself down to better and better results, more and more perfection. So, okay. and it's just an error thing, an actual mathematical thing, because you need to be able to know precisely, is this better in order to get to drive toward the direction of perfection. So a lot of this thing of like what will be solved is what has the most data, because I need to have a lot of data, I need to have a lot of compute around this particular domain. So programming has a lot of data. So then I can get to air quotes perfect programming. Some areas may not have a lot of data. Some aspect of finance or other thing may not have it. I need to create a approach to attacking that problem that uses a lot of data and where I get a loss function. Then I can solve it and get to potentially superhuman performance.
Okay, so loss, when you say losses, does that mean not using all of the data? Some of the data is not being used, or that there's some errors in
Right. If I give it a billion problems, right, and say, okay, and people say that was wrong, I didn't like that. If you got some like feedback thing where it says that was wrong, then it would say, okay, out of a billion questions, I had 2% that were wrong, right? If I get a more powerful system, I do a billion questions, I have 1% that were wrong or suboptimal or whatever. If they're not that good, right? So this is a mathematical way to guide getting to better answers and results.
Okay. All right. And maybe the last question on this slide, what are tokens again? What's the
So a token is, I think, 3/4 of a word, right? So it's just what they use to measure their data, right? So, a sentence of 10 words would be like 15 or 14 tokens or something like that. That's how they measure the information. So they say, here's all the words, the internet, and this is how much data there is there.
Okay. So about 5 to 7 keystrokes, something like that, maybe.
Right, something like that. Yeah, number of letters, 5 letters per token, that kind of. Yeah.
Okay. All right, then a different question. What happens to all these chips after they become obsolete? Is there what is the shelf life for these chips? You talk about all these chips being manufactured and deployed.
Right.
And then is there a secondary market for these chips?
Yes, there is a secondary market for used GPUs. So if you had a data center that only that had the gigawatt, you want the million best chips in there, then if you had the ability to uninstall and put in new chips, which is non-trivial, right? Because it took 90 days for XAI, the fastest installer of chips, to install their 100,000 chips. Then installing a million chips, they have to get faster and faster in order to get it done this year, right? They have to get 60 days for the next 100,000, 40 days for the next 100,000. Then that'd be 100 days. They got the 40,000 chips, and then they go faster and faster, 30 days to install the thing. So it's like a moving an army to do things, and then uninstalling them would also take time and effort. So it would be likely that they would then say, I will hand down my data center of old chips to someone else to resell it, and whether I move them, that's a business question of, do I want to take the time to move it, or do I need to have this location and need to do the transfer? Normally, you'd want to find some way to keep using them for 2-3 years, where it's like, I do training, the leading edge training, and I flip it over to the inference, answering a lot of questions on the thing. Not purely optimal, but so long as my energy, my revenue is greater than my cost of energy and operation, then I'm fine not being at the leading edge on that. So they will managing the use of a not leading edge GPU and getting more value out of it is a key business capability. I would expect XAI may hand off some of their chips to Tesla for the training of robotaxi and human and robot, right? So it's good enough to do that task, versus the leading edge they want for the AI model.
Mm-hmm. Okay, and maybe the last question. What vulnerabilities does the supply chain have? Are there enough technicians in places like Tennessee to install all of these chips so fast? Is that a constraint? There must be a lot of security around the delivery of these chips. These chips are very, very valuable. Also, is there a risk of counterfeit chips, chips that are made, by a counterfeiter that are
Right.
not really as good? So any vulnerabilities in the supply chain you want to talk about?
Yeah. There's all kinds of vulnerability in supply chain. I think it would be less of an issue for the big tech companies, like going from NVIDIA over to Meta, Microsoft, XAI, wherever, because they only have, they're probably dealing with a few big customers, so they would be sure they got them. It would be more of an issue, say, for potentially the counterfeit market, but it'd be so easy to check a batch to make sure they didn't get a counterfeit chip. China may have more issues around that because they have the ban, so they have to get chips routed through Singapore and other places in order to get them, and they may need to. But if you're dealing with billions of dollars worth of product, then if you get ripped off for a small batch, it's the supplier, the middleman, would be disincentivized to do that rip off.
Okay, and just the labor to install all
of
the
labor
chips.
Yeah. So again, going to the point where labor is a constraint. You'd have to have the people to do it. You have to staff it. But right now we're not at the point where it's like 10% of the labor force to do it. And I'm thinking Tesla will have 5,000 humanoid robots, Tesla bots, by the end of this year. Next year they're targeting 50,000 to 100,000. The year after that they're targeting 1 million. So we're going to transition over to this humanoid robot world in about 2-3 years. And there's like 80 other companies working on humanoid robots. There can be multiple winners there because you're replacing all of the labor. There's a fungibility on that market. You can find things, but then the fact that one company can succeed at $1 billion, $10 billion on that, who gets to the trillions? And then you're looking at, I believe, I can see who's going to win that. Probably other people can suspect who I'm thinking is going to win on the big prize. But that doesn't mean that investments and small guys can't do better. But yeah, we need to remove those bottlenecks using the AI and systems, how we design stuff, and then if we can build automation that can fix those things.
Okay, well, great. I think we can end the program here. We're very grateful to you, Brian, for spending all this time with us and educating us. I'm sure we all learned a great deal from your comments, so we really appreciate that. So good. We thank you so much for coming to us. That was Brian Wang, a futurist thought leader from Nextbigfuture.com. He's written over 30,000 articles, so you can read a lot of his work on Nextbigfuture.com. All right, so I think we're a little bit ahead of schedule. So I think we'll take a break for a few minutes and come back and we'll listen to a session of venture capitalists. So let's break for just about 5 minutes and then we'll see you in a few minutes.